Hi, welcome to the Shields Up Security webinar series from Microchip. Well, this is part of a series of webinars where we invite experts from multiple business units within Microchip, and in some cases outside guest speakers as well, to explore some security-related issues that plague a variety of applications and associated security solutions for those issues. My name is Todd Slack. I'm the product manager for our automotive security products within the Security Products Group, which is a standalone business unit within Microchip focused solely on security products and companion sorts of solutions. And today I'm going to focus on automotive network security, talk about some of the challenges that face us and some associated solutions. First, we'll talk about some of the motivations. We have seen a number of cool consumer-based sort of features. Traditionally, we think about Wi-Fi, hotspots, infotainment, the ability for kids to stream things with onboard Wi-Fi in the vehicle is all relatively new and very cool technology to add to vehicles, but it also represents a new entry point for the hackers. So every one of those new cool features that allows you to access the vehicle from an external environment is also added risk for a component that can be hacked from the outside world. Some of the things that we've dealt with over the years with some of the networks that have been adopted widely in the automotive space are that CAN 2.0, for example, has very small payloads, certainly nothing left over or very little left over for security in the payload with an 8-byte limitation. In the Ethernet world, we've seen a focus more on some of the traditional VLANs for traffic separation, not necessarily having security as the highest priority. We'll talk about how we can upgrade both of those sorts of pressure points. There have been no shortage of published hacks in the world against the automotive industry and others alike. There have been some that have resulted in recalls, which is an obvious monetary expense. There are lawsuits as well that we've seen around the globe. There's no single region that has been impacted by this. All regions and almost all OEMs to some degree have been impacted by it. And it is difficult to quantify tainted brand reputation. So it's important to have security in your system before you're hacked. So with that, we see a number of motivations to upgrade automotive security. And we see a number of different consortiums, organizations in the world that are producing specifications or best practices documentation for the automotive space to upgrade their security practices. In the CAN world, we are seeing a migration from CAN 2.0 to CAN FD, which does open the door up with some additional bytes available on the CAN FD payload, up to 64 bytes. And as we see more and more vehicles being connected, there is more push to get these vehicles and individual components upgraded to new OEM cybersecurity specifications. So in some cases, depending on the OEM, this represents a new generation of cybersecurity upgrades. Maybe they've had multiple generations of previous specifications where software solutions may have been acceptable, or there was only a focus on things like telematics. And now we see that focus broadening significantly. So we see some common security requirements in this new world that we live in. As I mentioned, there's no shortage of specifications coming from ISO and SAE, Auto ISAC, you name it. But those specifications are not directly adopted by the OEMs. So we see participation from the OEMs and tier ones and even tier twos in those organizations. But at the end of the day, each OEM has some slightly different pressure points and maybe historical architectures that they have to deal with. But from the common theme point of view, we see building blocks where the new security requirements will certainly depend on cryptography that requires you to protect your secrets or your private keys. And so that is central to some of the new requirements that we see in the OEM cybersecurity specifications. On top of that, then you can do a number of cool, secure things. First and foremost, we see a push for secure boot at multiple nodes within the vehicle. I'll talk about some of the reasons for that on some upcoming slides, and the ability to secure your field firmware upgrades. And then we also see that followed by many requirements for message authentication, namely on CAN, but not just CAN. We see message authentication with priority messages being required on Ethernet, you name it. It can even be sent out across RF. In some applications, we see that being adopted within the vehicle. So if we think about some attributes that would be good for the automotive space coming from an individual IC. As I mentioned earlier on the previous slide, clearly secure key storage is foundational. That allows you to then build on top of that secure key storage for things like CAN communication, where it's important to protect AES-based keys for CMAC. It can also provide a location for certificates. And while certificates themselves aren't required to be protected or encrypted, it's important that they remain in a trusted location and are available for verification and authentication in the system. Session keys can be generated by these types of devices, and so persistent keys should be stored within these types of devices, and then ephemeral keys can also be created to establish secure communication sessions. Trusted Ethernet nodes, if you think about Ethernet switches, can benefit from a secure boot, and then there's typically a tie-in to secure firmware update as well. And then TLS, transport layer security, we see is becoming more and more important at more nodes within the vehicle, and ICs that can support that stack can provide a benefit there. Ease of integration is clearly important, which really means how can I reduce the code development for whichever node I'm building in the system. So the less code equals lower cost, because that's faster time to market, and also reduced risk in terms of getting your security code implemented properly. And also allows you to have minimal change in many cases to the application code running on perhaps an existing microcontroller that you have implemented for multiple generations. Node authentication and key agreement. It is important to have some standards-based protocols there. And so if you can have these standards-based protocols in place, then you can also ensure interoperability so that multiple nodes in the vehicle can securely communicate and authenticate with each other. And then to minimize the impact in terms of performance on any given bus within the vehicle, it's important to have high-performance crypto accelerators. And so an IC that has that built in can provide minimal impact to any latency on any communication within the vehicle. And then finally, clearly in the automotive world, having an AEC-Q 100 qualification is important. I highlight here grade 1, simply because that covers the majority of the nodes that we are basically in communication with for tier 1s. That being said, there are also grade 2 nodes, and in the cases of things like the engine compartment, grade 0. But as a foundation, it should be AEC-Q 100 automotive qualified. So this is kind of expanding on some of the topics on the previous slide, but scalability is important. So if we can reduce the complexity to upgrade any given node within the vehicle, it does amount to some engineering time to upgrade any node, regardless of whatever solution you're using to upgrade with. So if you put the time and effort into upgrading one node, can that be repurposed in another node? The things that you learned on the one node in terms of integration and getting perhaps pre-configured devices can ease that integration and then allow you to add that same sort of security solution to a multitude of nodes, whether it is a high horsepower, high resource node like telematics or head units, or whether it's something simple like a rear liftgate ECU. Interoperability, that's where the use of standards-based cryptography is extremely important. The days of proprietary algorithms have been debunked. Understanding that the more eyes that you can get on an algorithm, the more comfortable you can be in its security. And so if you use those standards-based algorithms, then not only do you improve the level of security, but you also improve the level of interoperability, meaning that a multitude of tier ones can select a wide variety of tier two silicon solutions. And at the end of the day, those ECUs, when they're plugged into a vehicle, can interoperate with each other and securely communicate for things like message authentication. Maintaining existing performance is important, which kind of ties back into that hardware crypto acceleration point, in that you have many dependencies on performance on different buses within the vehicle, some different expectations about when a given ECU is required to start communicating on any given bus. So it's important to minimize the cryptographic operational times. Hardware protection is clearly important. We, 10 years ago or so, used to have some debates about whether or not software was good enough. And with many of the public hacks, there's less and less argument about that, in that in order to have security, it really comes down to how well you protect your keys. You need to protect them in hardware, not software. As you think about the dependency on keys and protecting keys, at some point you need to generate keys. And the provisioning process can be difficult for some tier ones who may not have that infrastructure in place. It can even be difficult for some tier twos. So if you have provisioning services in support of security ICs, that can really simplify things in terms of the back-end process, getting keys generated and securely either internally generated inside of a device or having some keys uploaded from an externally generated source like an HSM security server. And then preserve legacy where needed. It is important that you can upgrade your nodes with minimal impact. And in some cases, that means that you would still like to use an older MCU that may not have the security requirements in place that are now being mandated by the new OEM cybersecurity specifications. And so if you can simplify that upgrade, maybe protect that inexpensive purchasing channel through your procurement and using a companion IC sort of solution, then you can upgrade and preserve those sorts of contracts. So I mentioned hardware-based security. What exactly does that mean? Well, it starts off with an active shield over the entire surface. In some cases, we do see many shields, but the preference should be an entire active shield across the entire chip. So if you look at the lower right, there's a microscope shot of a standard microcontroller where you can see that you have access to non-volatile memory, data lines, and in some cases, access to test probe pads that are simply not bonded out as the strategy for security, where it would be simple to drop a microprobe down on that and get access to test mode, for example. The upper right, you can see a zoom in of a small section here of this little red box where you can see some serpentine metal. And that's an active shield so that you can prevent anybody microprobing those data lines or non-volatile memory and determine whether or not that shield is intact. So if somebody tried to cut that shield to drop down microprobe points, then a proper security IC would detect that that shield has been compromised and go into protected mode. Second step behind the shield is that you should internally encrypt the keys themselves, so that if somebody spends enough time and money to try and trick a shield into thinking that it's still intact and open up a little window into where they think the keys are stored, then those keys should be internally encrypted. When we talk about randomized math operations, data crypto execution, those are some strategies that can tie into protections against differential power analysis, where you can monitor a device's use of a private key, say for a signing operation, thousands of times. And then you can actually extract information, if not the entire key, from those differential power analysis attacks. So if you can do some things in a slightly different order each time, you can protect yourself against that. There are attacks that involve fault injection. So detecting that fault injection with internal state consistency checking is important. There are many historic attacks over the years that involve reducing the voltage and the temperature on a device to get it to misbehave. You can think of putting the device in a lethargic state. And in a good security device, it should have some environmental tampers in place to detect those out-of-spec conditions. And similar to cutting the shield, the device should detect that it's in this out-of-spec condition and go into a protective mode where at minimum it would no longer cooperate with cryptographic activities until it's back into an acceptable safe state. Internal clock generation helps prevent anything like single stepping the clock, and that's considered good hygiene security products. And then it's important on dedicated security products to not have the same level of testability that you have on your application products like MCUs, because testability and security are in absolute opposition to each other. So the beauty of having two-chip solutions where you can have a host MCU or MPU or FPGA continue to focus on the application that it supports and maintain the testability that the engineers are used to with those sorts of devices, and then separate your security functions to a dedicated security chip that does not have JTAG, that can provide you a higher level of security for key protections is important. Secure boot and firmware update. These are the first things that we see added to OEM cybersecurity specifications. Secure boot, the motivations are fairly straightforward in that you would like to verify that the code that is resident on your host is trusted when it's loaded, and you can verify that trust by verifying signatures of the incoming payload, either in the factory or in the field. And then every time that you have a power on reset event, you should verify that that code remains in a trusted state and nobody has tampered with it or added a malicious code to it. In many cases, nodes within the vehicle and ECU will have a prescribed startup time, and that it needs to start communicating on the bus after power on. So say some node has to start communicating within 100, 150 milliseconds. Depending on the size of the application code and the resources of that particular ECU, you may determine that you don't have enough time to validate 100. And so having a level of configurability in your secure boot scheme is important, so that it's terrific if you can validate 100% of it, but maybe it's not always practical, and therefore it can be beneficial to have the ability to partition your code, which would allow you to verify a certain percentage of it based on how much time you have for the boot process, and again, the resources that you're working with from the host, and a companion solution perhaps. And therefore, you could validate a certain percentage of that code, and if it looks good, you could power on and start communicating on the bus, and then in the background go complete your code validation. But having configurability is important because different nodes will have different sets of requirements, and so being able to be flexible in that implementation is important. So here I'll show you an example of how you might upgrade an existing ECU today that is based on an MCU that maybe only has CAN 2.0, and yet your system is moving toward CAN FD where you have more bytes available for message authentication. So in this case, we'll show how we can insert a security IC in between host microcontroller and a CAN FD transceiver. And we are kind of skipping forward here in the animation on the coming slides beyond the point where we've had the shared secret communicated to all of the nodes that are supposed to care about each other's messages. So when I say care about each other's messages, I mean that they should have cryptographic message authentication code generation and verification capabilities. So when I go back several slides, we were talking about using standards-based cryptography. This is where it's also important to be able to use standards-based cryptography to get that shared secret into multiple nodes. You can do that in a variety of different ways. It can be through EC Diffie-Hellman. It can be through EC Burmeister-Desmet, more of a group key agreement scheme, or you could have a gateway within the vehicle responsible for key generation, and then it could wrap those keys with each one of those nodes public keys, and so you can protect the transmission across the bus and send out the same AES key to each of the nodes that care about each other's messages securely. So we've done that here, and now we show that the host microcontroller can generate a CAN 2.0 message. This is just one example. You could certainly do message authentication via RF or Ethernet or other. But in this case, we're showing CAN 2.0 to CAN FD conversion, where you could have a security IC that's capable of generating the MAC associated with it. If you think about the messages within a vehicle and look at a variety of OEM specifications, not every single message will require message authentication. So you should have a lookup table in that security IC to determine whether or not that device and that specific message needs message authentication code. So assuming it does, then the security IC can use that AES key that I just mentioned in the previous slide to generate a message authentication code across that initial CAN 2.0 message, while also incrementing a session or sequence value. In some documentation, they refer to that as a freshness value to prevent replay attacks. And then you can send that across the bus. On the other side, do what you might imagine is the verification operation, in that you can have a security IC or some other solution. Maybe now, in this case, you have an on-die integrated multi-core MCU that is using the standards-based protocols that I mentioned, in which case you could also perform the same verification. But here we show that we have that shared AES key used to verify the incoming message authentication code. If the security IC approves and verifies the message authentication code cryptographically, it can pass that message back to the host MCU to act upon. If not, then it can simply discard the message and not act upon it, and perhaps increment a counter for failed authorization. And at some point, you could set that threshold to some number where it ultimately ends up, say, a check engine light coming on in the system. You're getting a high amount of unauthenticated messages. So if we look at an existing CAN network here, showing vehicle bus with mixed implementations, we have 5 different ECUs. And to begin with, we're looking at CAN 2.0. And if we need to communicate in a secure way, meaning message authentication, we can do a number of different things to upgrade that specific ECU. And so here I'm showing an example of how we might upgrade ECU A and E with a security IC that can convert CAN 2.0 messages to KE and vice versa. And then here you may have ECU B, where they have decided to get a new host microcontroller, and this host could benefit from having a dedicated security IC, perhaps communicating across SPI or I2C to it. And then it has the direct connection to the CAN FD bus. And we can also look at solutions where we can now communicate with a mixed ecosystem. So you could have some CAN FD based MCUs, some CAN 2.0, a mixture of security ICs hanging off a variety of communication protocols with each of those hosts, and you now have the ability to securely communicate. ECU C and D were straight CAN FD to begin with, and perhaps they had some integrated security already in a multi-core solution. Now you can also talk with those nodes as well. So you're looking at 5 nodes on a CAN-FD bus, all with very different security implementations, but with some common protocols and cryptographic algorithms that can allow them to communicate with each other. You can have different tier ones building different ECUs, and at the end of the day, you can proliferate and add and upgrade security to any ECU using any MCU or any MPU or even FPGA for that matter. So a multitude of tier ones can work with a multitude of tier twos, silicon provider, and act harmoniously in a secure way within the vehicle, in-vehicle networking system. So continuing with configurability, it's important that you can configure your CAN-FD frames in this example differently depending on which OEM you're ultimately supporting and which solution they've gone after. So in some cases, we're looking at some unique implementations. And if your security device is capable of supporting that configuration in terms of MAC, could be 16 bytes, for example, it could be 12. The freshness value or sequence counter, be 4 bytes, could be 8, could be 1. Having that configurability allows you to support a variety of specifications, whether it's coming from AUTOSAR, JASPAR. In fact, JASPAR is even focused on adding security to CAN 2.0 8-byte payloads. So if you can configure your payload and your frame format, then you can support any variety of frame formats. And in this case, I'll show you now we're moving to the AUTOSAR frame format. And so if you can have the same device support different formats, obviously that provides the most flexibility for adoption, the widest variety of ECUs that tier ones are building. Hardware secured TLS. In this slide, I'm showing how you can offload all of the heavy lifting to a security IC, which means that the keys can be generated and protected in that security IC with all of the hardware-based security mechanisms and tampers that we mentioned in some of the previous slides. And in some cases, especially depending on the resources available on your node, it may not be practical for that host to implement a full TLS stack. So if you have a dedicated hardware security device that can take on the majority of that stack and simply have the TLS API resident in the host MCU, then you can now establish transport layer security sessions even on very small resource nodes. We look at some of the requirements that we are seeing out there. SAE J31, J3061 gets a lot of consideration. You can go to a variety of conferences around the globe in different regions, whether it's Asia, Europe, or the Americas. And this gets a lot of attention. This is getting folded into the ISO 21434, but ultimately it has some inclusion where if you're building a component for a vehicle that's connected to a bus, that you should perform a risk assessment to determine how a hacker could enter that node, and then an attack tree analysis to determine what other nodes that they might get access to if they break the ECU, break into the ECU that the tier one has built. And then the third component is to have some written justification for your security implementation. And so while these specifications don't mandate the hardware security adoption, the process generally ends up with, at minimum, an internal education that determines that if you don't protect your keys and hardware, that it's difficult to have a written justification that you've done anything smart for your security implementation. So, in summary, we've got three main components in the security world, and this is automotive centric today, but also applies outside of the automotive world because we're facing with the same security concerns. But secure key storage, again, central to everything. You got to have hardware-based key storage to protect your secrets and your keys. Secure boot is phenomenally important to make sure that the nodes within any given network are functioning in a trusted state. and that they can also be securely upgraded as you see either feature upgrades or bugs that you'd like to patch. It's important to be able to upgrade those in a secure fashion based on signature verifications. And then finally, we see the major component in the automotive security space to upgrade to message authentication, make sure that the communication within the vehicle is coming from a trusted source before you act upon it. So scalability, important, again, just in review, to be able to come up with a security solution that is easy to proliferate across a multitude and wide variety of ECUs. Interoperability allows you to ensure that many different vendors can have solutions, and tier ones can select from those solutions and guarantee that there is interoperability across all of those tier ones in a vehicle with different ICs that have been selected. Performance, again, goes back to the cryptographic acceleration to minimize the impact of the increased performance or increased calculation time for security in the system. Got to protect your keys and hardware. Provisioning can be a major burden, so having an IC that has the support in place to support all of that back-end infrastructure associated with secure provisioning is important. And then minimizing the impact on your upgrade allows you to preserve some of your legacy contracts and maintenance. So with that, I thank you for your time and attention, and to this Shields Up security webinar focused on automotive security. We have a number of webinars that are already out there on YouTube and more that are coming. So please stay tuned to microchip.com and check out our Shields Up security webinar series, past, present, and future. Thank you.